So I begin by thanking the organizers for organizing QMAT in its largest scope and to see most of the condensed matter community together in the same venue. So this work is about valid drag, a comparatively new phenomena on Moire systems. Most of the technical part of the work is done by Rita Jit, who is also somewhere in the audience, and this is in collaboration with Mandar from TIFR and Harv Partik from Indiana. This work is now in archive. Okay, so what is a drag or Coulomb drag? So if two-dimensional systems are brought very close together, then the electrons can feel each other from the two different layers through Coulomb interaction. And if one drives a small current through one of the layer, such interaction leads to a development of voltage across the other layer. Okay. It's like a viscous drag in liquid. That's why the word drag comes in. If the two layers develop strong interlayer interaction, then drag can become anomalously large. Also can dictate can be a probe of interlayer strong correlation. It's a very useful kind of many body effect that one can see in experiments, and there has been many experiments. These are recent ones in two-dimensional systems, this kind of bilayer systems. So how it works? So technically, these are I am driving a current in one layer and I am seeing a voltage in another layer. So these are technically current correlators. It's a theory talk. I should be clear on this slide. So microscopically, what happens is that if you drive current through one layer, it gives rise to small change of densities on that layer, and that small change of density introduces effective potential to the bottom layer, which the bottom layer can fill and translate into a current or a voltage in the bottom layer. So it's a typical Coulomb drag is related to fluctuation dissipation theorem. Just to say, Srinjoy has a poster on non-equilibrium fluctuation dissipation theorem that you can see later on. So technically, these are current correlators, and if one expand in interaction strength, the bilayer interlayer interaction strength, so they come in first order, second order, and so on. There are three facts about Coulomb drag. These are fluctuation driven phenomena. So at t equals to 0, the drag goes to 0. So it needs to have a small amount of thermal fluctuations of each of the layers so that the drag can happen. Now, because the thermal skin of thickness kBt happens around Fermi energy each of the layers, the typical Coulomb drag is of the order of kBt square. So it goes to 0 quadratically at t goes to 0. These are of course when I am talking about typical metallic systems. Interestingly, the first order contribution also cancels exactly, and that is because of time reversal symmetry. So the something like a forward and backward drag exactly cancels. So the Coulomb drag is 0 at t equal to 0, it goes as t square and only appears in the second order process. So it's a fairly weak phenomena, in the sense that you drive a current, the voltage you develop will be a small amount. Now, I will be talking about phenomena similar to this in Moire system, and Moire has been introduced I think by all the last three speakers. Nevertheless, let me give a 2 slide of things that are important for this particular talk. So Moire systems are two-dimensional materials which are twisted by small angle. So the resulting 2D system, the hybrid system now has new lattices which much larger lattice length. The band structure gets folded essentially. As you make the real space lattice larger, the Brillouin zone becomes smaller. So you fold your original real space lattice, original untwisted band into the twisted band. So it becomes many bands in the twisted Brillouin zone. crucially, the Moire length is often much larger than the interlayer spacing, and that is important for the physics we will be talking about. So, in typical cases, if you have atomic systems, then you have two layers close by. The separation between the two layers would be larger than the atomic separations. But for Moire systems, the separation between the layers can be smaller than the Moire length scale, and this is important for the physics we will be talking about. So, in what happens in momentum space, we have graphene as valleys. So, if two graphene are twisted and placed very closely, in momentum space, the Dirac points of one of the valley are now placed very close from the two layers, and if one introduces some interlayer hopping, then these the bands where they cross between the layers, they open a gap, and by tuning the interlayer hopping, one can get into various interesting physics, as we know, like flat band. Even more, the other side of this is that even though these are coming from the same valley, they can have non-trivial topology, although it's called fragile topology. Part of the reason is that you have to take into account the fact that there is another valley sitting there, which will have exactly opposite Chern numbers. So, the net topology might be 0, net Chern number might be 0, but individual bands can have topological nature, they can have Betti curvature and so on and so forth. So, it gives a whole plethora of physics coming from flat band and strongly correlated physics to Betti curvature driven physics and so on. So, we have been working on the system for some time now. So, we looked at with theory as well as experimental collaboration to non-trivial transport because of topology, trilayer graphene, twisted Weil system, twisted high TCs. We recently have a review to appear in Nature Physics very soon. Now, the valleys are interesting. So, these are a hidden degree of freedom. So, you can think of these are like a spin up is k valley and spin down is like k prime valleys, and they are related by time reversal symmetry. So, these allows a valley current J plus minus J minus to be present in principle in a drag, in a Coulomb drag. So, even though the charge current is 0 because of time reversal symmetry, because what happens, the two values from the two the Coulomb drag from the two values exactly cancels, but if one calculates the drag of the difference of current between the two values, that can be non-zero. Interestingly, it turns out that this is also 0 at t at q tends to 0 because it becomes an integral over Fermi surface derivative and that vanishes. So, one has to do more. Not only just a valley current can have a Coulomb drag, one has to do more to make it possible to see at low wavelength. So, let us look at the structure a little more carefully. So, a interlayer conductivity has a form like this, where have the skies are current density correlation functions. Okay, the exact structure is not important, but the fact that the sky for a valley, essentially this becomes this integral over Fermi surface. Okay, and what is important is that the integral of, because it's integral over Fermi surface and not an integral over a Fermi surface derivative, this in principle can be non-zero at t equals to 0. So, it's not a fluctuation driven process, and finite temperature there will be t square correction to it. The lambda sitting here is very important. This is the overlap or structure factor, which kind of measures how much the electron leaves at which value of g. The g's are reciprocal translation vectors. So, in a block system, I have the block momentum k, but the wave function of the electron leaves within the unit cell with some probabilities. Okay. So, these are the component of u n k g, okay, and the unit cell becomes important, as we will see in the next slide. Now, this chi for a Coulomb drag, typical charge Coulomb drag has a form like this, and chi for a valley drag, which is j plus minus j minus, has a form like this. And the time reversal symmetry is very easy to see that this makes the charge drag to be completely vanishing without any further condition. at t equal to this or t equal to 0. But the valid drag can survive because of extra xi factor. So, essentially the charged drag vanishes because the k and k prime valid drag exactly cancels each other. The valid drag can be non-zero because k and k prime they adds up. But this still requires g not equals to 0 contribution, and otherwise the form factor lambda will be simply identity, and this will also kill the valid drag. Okay. So, I know it is a bit of technical statements involved, but let me summarize what I said. So, the question is, how can I have a first order Coulomb drag at t equals to 0 or first order drag process at t equal to 0. So, Coulomb drag is never possible by time universal symmetry. If we have time universal symmetry, we can have valid drag in principle at t equal to 0, but this would require q not equal to 0 process. So, how can you have that at low wavelength? Is by Umklapp processes, where my exact amount of momentum transfer is reciprocal lattice vectors, which does not really change the system. It is like translating the whole system in momentum space by one reciprocal lattice. In atomic crystal, G is large. So, the Umklapp driven Coulomb drag would be vanishingly small, because it will be suppressed by exponential of G times D. D is the interlayer separation. In Moire, the trick is that the Moire, the lattice reciprocal lattice is small. So, the reciprocal translation vectors are small. So, this allows this particular factor to be not negligible anymore. Okay. So, this is how it works for Moire. So, it is a summary of how things change for Moire. So, if a Umklapp driven process, this is not anymore a fluctuation dependent process. It is not a fluctuating because it is not a thermal fluctuation driven process. So, it can be non-zero even at 0 temperature. And the cancellation because between k and k prime values, this can be dealt with if we are talking about valid drag and not charge drag. So, the j plus minus j minus times rho, this will remain finite by time universal symmetry. Okay. Now, let us look at how this comes out for a given system. So, we did some numerics with a graphene HBN setup, where I have a graphene, an HBN and a graphene, and the two graphenes are perfectly aligned. It is called double aligned structure. As many of you have heard, that because of the HBN and the lattice on top, they have small lattice mismatch, and this can give rise to interesting Moire like structure. For example, graphene and HBN has 1.8% lattice mismatch, and that gives us a super lattice of Moire with a Moire potential. The subtlety is HBN is buckled in the sense that it's not exactly in 2 dimension, it has small variation in the 3rd dimension. So, the graphene on top and graphene on bottom can see the potential slightly differently, but if they are perfectly aligned, nevertheless the reciprocal translation vectors are exactly same. So, you can transport that amount of momentum from between the layers. All right. So, this is one of the plot we have. So, if one does the numerics, we can see that the interlayer conductivity or drag conductivity that goes to a finite value at t goes to 0, and it deviates at second order in temperature. So, the second order one can easily figure out from doing a Sommerfeld expansion, which is typically valid if you are not sitting very close to a Van Hoff singularity. I mean, the system do have Van Hoff singularities, so you have to be careful. Very close to Van Hoff singularity, you can have more non-trivial temperature dependence, which I am not showing here, which itself is interesting aspect. But away from Van Hoff singularity, you will not be dealing with such a non-trivial temperature dependence, and you can do Sommerfeld expansion safely, and you can show that the value the drag goes as t square. As a function of the spacer separation, that means the interlayer separation, it goes exponentially as we expect, and it goes exactly with the first reciprocal translation vector. I mean, this is one of the indication that this is exactly happening because of Umklapp process, that the exponential picks up the factor minus g times d. And as I mentioned, this G times D would be much larger for a typical atomic crystal, because the D would be several times the typical unit cell lattice length scale. So, this is not going to be essentially measurable for a atomic bilayer system. Okay. So, what happens in the Moire system is that the G becomes much smaller. So, the G times D can become of the order of 1. Here is of the order of 0.5 in terms of real numbers, the numbers we are used. Now, there is one real issue of doing this experiment, which is the double aligned structure. So, the physics here dictates that you are transferring exact amount of momentum, which is the reciprocal translation vector, from one layer to another layer, such that none of the layers are being affected by it. But this requires the two layers to have perfect Moire structure, and as we have just listened to, that is never possible. There will be structural deformation, there will be angle inhomogeneity, and so on and so forth. So, typical momentum space Fourier FFT will show you not a very sharp peak, but a broadened peak of the structure. Okay. This shows that the typical these Moire systems are never perfectly homogeneous, they have inhomogeneity, and these are inbuilt, these are not disorders. So, if the two peaks are not perfectly sharp, then that actually helps us. So, if the two layers are not perfectly aligned, that means that the two peaks will not be falling on top of each other, and this whole physics will be lost. But if each of the peaks are now broadened, then even though they are not perfectly aligned, there will be overlap of the peaks, and through which the momentum transfer can take place. So, even if the two-dimensional system is slightly misaligned because of the structural inhomogeneity of the system, we will still have a probability of such process taking place. So, one can do a simple modeling of the broadening of the Bragg peaks. So, one can write down the delta function in terms of these etas, and one can see that the change of conductivity because of the broadening of peaks will be of the order of eta square. So, it is kind of, it decreases from the predicted theoretical value, but it does it in a more slow manner. So, it does not completely go away. Now, if the broadened peaks do not overlap at all, if the misalignment is such that the broadened peaks are very far from each other, then the first order will be 0 and will be back to normal Coulomb drag of second order. There can be also perfectly aligned systems which are possible now, and this whole physics is not restricted to graphene and valley drag. In TMDs, the valley current would be same as the spin current, and then the valley drag there would mean a spin drag. This how to observe it. So, the setup we propose is this two layers where one drives a current in top layer in this manner, and because of the Berry curvature of the top layer, this will give rise to a valley current on the top layer. So, this valley current top layer will introduce a valley drag current in the bottom layer, and because of inverse Hall effect, this will give rise to a voltage in the bottom layer. So, the separation of the current and the voltage probes are in such a way that we specifically do not want Coulomb drag to interfere.
5 minutes.
Yeah, I am almost done. All right. So, this is the proposed setup is yet to be realized. Now, the few comments one can have that as I mentioned how well the alignment can be, the double aligned structure is becoming more and more common. These are some of the works. The club, how strong it is, and is it the bilayer interaction, and is it tunable. So, this particular work talks about even controlling club scattering through electronic manner. So, these are club is a process that now people are talking more and more in the Moire systems. And valley is hard to observe because we have to do this Hall effect and inverse Hall effect to observe a valley current. If you have TMDs and twisted TMDs, then there's a whole valley current terminology will go into a spin current terminology for TMDs, and which are easier to observe. Just to summarize, so we mentioned discussed how typical Coulomb is second order process and vanishes as T square. Valley drag is a uniform system is not related to that, but it exact cancellation happens for uniform system without without a G, so without a structure within unit cell. The Umkla process allows us to have valid drag at t equal to 0 and at first order. So it's observable via valid drag readouts, tunable by twist angles, a lot of physics to explore in future. These are the funding support we have. Thank you.
Thanks, Mr. for a very nice talk. So the session is open for questions.
Hi, Abhijit. So one of the features that you are using to get this signal as substantial is the fact that the Moiré lattice constant is much larger than nuclear separation. That gives you the thing. But what I am worried about is what is the U that you are using? Because is it the projected U on that band, or are you using the bare U? Because the point is, yes, I mean the Moiré lattice is much larger. That's why there is band zone folding and the G gets smaller. But so does the U if you project it appropriately.
So there are two U's. One is U is within the intra-layer U. Okay, of course that has a strong suppression. Then there is this interlayer U, which is also gets suppressed because of the charges present along outside. So we do take into account the effect of screening. The values.
I'm not talking about screening. I'm talking about projected U on the band that you are interested in.
Right. So you are right. So in this work we have not used a projected U. We used a bare U, but we used the screening. But in principle, you are right. The projected U will become even smaller.
That number might again become small. Whatever you
That's
are
true.
gaining from e to the power minus
That's
might get compensated by a smaller U here.
That will be overall factor, not the exponential term. There will be overall factor because as Q tends to 0 fact. So, and the same suppression happens for bilayer metallic drag experiments, and the numbers are not far off from typically what you will get for bilayer drag conductivity. It can get a little bit suppressed, but I don't think it will be dramatically suppressed. But we have not taken a projected U on the band.
And the other, just a quick question, is this Fermi surface integral?
Right.
You're making a distinction between Fermi C and Fermi surface, right?
Right. So the Fermi, typically what happens is that you can have integral over derivative of Fermi surface. Okay. And these are typically what you have for fluctuation dependent processes, right? And these will go to 0 at t goes to 0. If you have a Fermi surface integral, there is nothing that stops it from being non-zero at t goes to 0. So a Fermi surface integral is not a fluctuation dependent process. That's how you can think of it.
I'll talk to you.
Absolutely.
Thanks.
Nice talk. When you make this statement that t is equal to 0 limit, it should work. Okay, I'm wondering that t is equal to 0 limit, the electron scattering will diverge. Even though you are very close by, your electron scattering is almost much bigger than system size.
Correct. Yeah.
So how do I see that? I mean, if they don't scatter, even the Umklam is there, why there should be any drag at all? There is momentum transfer between the two layers.
Right. So what happens is the following. You see, actually the electron never leaves the momentum because the k and k plus g are both present at its block state. Okay. So the system remains as it is if you allow transition symmetry to be there. Okay. So the process is like a amplitude at k and amplitude on k plus g. There is a scattering within the same block state, and the corresponding scattering in the bottom layer between the k plus g to k, but electrons themselves do not really scatter.
Oh, I see. So look at, they don't, between the two
No,
layers,
no, there is no scattering. Between the two layers, absolutely no scattering.
I mean, by Coulomb interaction, there's scattering. Typically,
Within the same, okay, the momentum transfer, typical Coulomb drag also, the electrons on top layer transfer within the top layer, electron bottom layer transfer within the bottom layer, but the two processes are correlated by Coulomb interaction.
but there is an interaction between the two layers.
Yes, but it doesn't allow electron transfer between them.
So you are saying there is no, but there is a
No
momentum
hopping.
transfer from one layer to other layer, right?
But those will be suppressed at larger d. So these are in the, and that's kind of boring if electrons can really transfer between the two.
But origin, see the point that t equals 0, 1 over tau is infinity.
Yeah.
Right.
So where is this interaction going to happen? The self energy is T square, right?
Right. So again, you're thinking of thermal processes. Electrons are never. This is precisely the point. You see, if I have a thermal fluctuation dependent processes, then I need to have small pockets of electrons around the Fermi surface, so the electron can actually scatter. A Umklapp process is not a fluctuation dependent process. So electrons are never really scattering. Is the amplitude within the same block states, amplitude of k and k plus g are getting connected to the bottom layer k and k plus g. It's an Umklapp process. Okay, that's precisely the point. This is why this is not a FDT. It's not related to FDT.
Any more questions? Students? Okay. If not, then let's thank